Hey guys, in this video we're going to do a couple of examples of anti-differentiation. First of all, we should do this one. So we should find the antiderivative of the function f of x equals x to the power of n. Well, when we differentiate a function, we subtract 1 from the power and multiply by the old power. If we go ahead and do the opposite of that, by adding 1 to the power and dividing by the new power, we find that actually, yes, we get exactly what we want. Because when we differentiate this thing, we're going to bring m plus 1 down to the front, and then that's going to cancel with the m plus 1 on the bottom, because m plus 1 divided by m plus 1 is 1, because anything divided by itself is 1. So we get rid of that, and also we're subtracting 1 from the top, so we're actually just left with x to the power of n as we wanted. So we found one function that differentiates to give us x to the power of n, but we want to find all of them, and we worked out in the first video that all of them actually differ by a constant. So if I just add on some random constant c, some arbitrary constant c, that's going to give me all of the functions that differentiate to the function x to the power of n. So that's a pretty handy rule to know. It's like the reverse of the power rule in differentiation. Now, putting this together with the other rule that we learned in the last video, we learned that anti-differentiation is linear. In other words, the antiderivative of k1y of x, k1 f of x I called it, k1 little f of x plus k2 little g of x, the antiderivative of that with respect to x is equal to k1 times the antiderivative of little f of x plus k2 times the antiderivative of g of x with respect to x. So that's what we learned in the last video. Combining that with what we're going to call the reverse power rule here, we can actually find the antiderivative of any polynomial we like. For example, let's go ahead and find the antiderivative of 3x to the power of 7 plus 12x to the power of 4 plus 10x squared dx. Well, from our observation or our calculation or whatever, our proof that anti-differentiation is linear, we can bring all those constants out the front of the antiderivative signs, and also we can split up the antiderivative signs over the pluses. So that's exactly what we're going to do. Therefore, this is equal to 3 times the antiderivative of x to the power of 7 with respect to x plus 12 times the antiderivative of x to the power of 4 with respect to x plus 10 times the antiderivative of x squared with respect to x. And now it's easy because we just apply the power rule that we just learned. You add 1 to the power and divide by the new power. So this is equal to 3 times x to the power of 7 plus 1. So 3 times x to the power of 8 divided by 7 plus 1, so divided by 8, plus 12 times x to the power of 4 plus 1, so 12 times x to the power of 5, divided by the new power, so divided by 5, plus 10 times x to the power of 2 plus 1, so 10 times x to the power of 3, and again we divide by the new power 3. And of course, we need to add on our constant of integration, little c. So, by combining these two rules here, you can actually find the antiderivative, the set of all the functions which differentiate to polynomials. You can find the antiderivatives of polynomials by combining those two rules there. All right, thanks very much for watching. Don't forget to check out the notes that go along with this section and have a go at the exercises at the back. See you next time. Bye.